Welcome back to our Chem 152 video series. In this video, we'll be talking about how to use the small x approximation to make solving reaction tables easier. This reaction starts with acetic acid plus water and yields C2H3O2 negative plus H3O positive. We are given that we're starting with a 0.10 molarity solution of acetic acid. We are asked to find the equilibrium concentrations of all the species at the end. We'll begin by writing initial change in equilibrium lines for our reaction table. There are three critical pieces of information anytime we do a reaction table problem: the initial conditions, the change, and the equilibrium constant. Here we were given the starting molarity for acetic acid. We were not given any molarities for the products, but we can safely assume those are 0 because they're not given. And so we know the initial conditions. We are also given the equilibrium constant, so we know that as well. The thing that we don't know is the change, so we will let the change be our x. We always react toward the zeros anytime we do a reaction, so we will lose some of the reactant and gain some product. Therefore, our equilibrium concentrations may be written as 0.1 minus x for the acetic acid, x for the C2H3O2, and also x for the H3O positive. Before we go any further, let's discuss the small x approximation. The small x approximation states there's a shortcut we can take in the math as long as the k value is low enough. The reason for this is because if the k value is low enough, we won't make very much product and we will hardly use any reactant. Recalling that the k value represents how favorable the reaction is, and so if this reaction is not very favorable, we won't use very much of our starting material at all. The small x approximation tells us that we can remove any plus x's or minus x's from the equilibrium concentrations. However, we do have to keep any lone x's or multiplied x's in the equilibrium concentrations. What this means is that when we write our equilibrium constant equation, this 0.1 minus x becomes just 0.1. We can safely ignore the minus x. However, these x's that are by themselves, let's keep those where they are. Any lone x's or multiplied x's stay the same, but plus x's and minus x's we can ignore. The reason why this is useful is because when you construct your equilibrium constant equation, you'll see that it's much simpler than before. Let's write the equilibrium constant. My k value for this reaction was 1.8 times 10 to the negative 5. This will equal the products over the reactants. My products are C2H3O2 times H3O. This will be divided by the HC2H3O2 acetic acid. Both of my products are just x, so I can write this as x times x. And on the bottom, I no longer have to write the 0.1 minus x, I can just say 0.1. If I rewrite this equation, now I have 1.8 times 10 to the negative 5th equals x squared on top and 0.1 on the bottom. The reason why this is important is because this form of the equation is much easier to solve than the problems we did previously. Our previous problems oftentimes used the quadratic formula, and for this question, this won't be necessary. What we need to do is take the 0.1 from the denominator and multiply it over to the left side. We will end up with 1.8 times 10 to the negative 6 equals x squared. And now all we need to do is take a square root on both sides. When we take the square root, we'll get the value for x. And on the left, we can just use the square root function in a calculator. Our answer will be 0.00134. Therefore, we can say that our final concentration for C2H3O2 was 0.00134, and our concentration for H3O is also 0.00134. And we can say that our final concentration for HC2H3O2, acetic acid, is still 0.1. Bear in mind that it's not exactly 0.1, but our x is so small that it's still close enough to 0.1. Here, I've used a graphing utility to find the value of x we would have gotten if we had used the quadratic formula. The graphing utility gives us an answer of 0.00133. Notice this is very close to our value of 0.00134, which we got from using the small x approximation. You'll note that the value is not perfectly right, but for most of our purposes in Chem 152, it will be close enough. In general, there's a guideline that you can stick to. Usually, if the K value is lower than 1 times 10 to the negative fifth, you are generally safe using the small x approximation. This is not necessarily a hard or fast rule for this course, it's more of a general guideline. Be careful about using this rule when you are close to 1 times 10 to the fifth. The higher your K value is, the less reliable the approximation is. In chemistry, there are always going to be cases where the guidelines don't apply. If you're ever in doubt, it's always better to check using a graphing utility or a calculator. While the small x approximation makes our math on paper easier, it sometimes gives us misleading answers if we use it at the wrong moment. So be careful when you choose to use it and when you don't use it. And make sure to take a careful look at the K value before you start. Thank you for watching, and we'll see you again soon.